Hello everyone. Today we are going to discuss a new topic. It's simply a very small topic known as Stirling's formula. Why are we discussing it? The reason is that this formula, the expression given by this formula, is used in many physics derivations. Specifically when we derive the concepts from statistical physics and thermodynamics, in those concepts we make use of this formula, which is Stirling's formula. This was given by Scottish mathematician James Stirling. So, whenever we use big derivations to solve larger factorials, we don't go for solving all those factorial. We simply make use of Stirling's formula. So, this is a formula based on factorial. And what is its use? It is used to analyze larger factorials, to analyze the value of larger factorials. Now you know how to find the factorial. Suppose we have a number 4 and we have to find its factorial. How do we do that? First, we take 4 and then we multiply it with the number which is obtained by subtracting 1 from this number, the given number. So what is 4 minus 1? We have to find its factorial again. So basically this is 4 into 3 factorial. And then again, since factorial is there, so what we will do, again 4 is fine. Now for 3, we will write 3 as it is into the number which is obtained by subtracting 1 from this particular number, whose factorial you want to find. So that is 3 minus 1 factorial. So that gives us 4 into 3 into 2 factorial. Then again, since factorial is there, we have to continue solving. So we will do 4 into 3 into. Now the number itself, whose factorial we want to find. So that would be 2 into the number which is obtained by subtracting 1 from the number whose factorial you want to find. So that would be 2 minus 1 factorial. And that gives you 4 into 3 into 2 into 1 factorial. And then again, since this is mentioned that we have 0 factorial as 1, so what we will do, 4 into 3 into 2, because these are simply numbers now. And now 1's factorial we have to find. So first we will take the number itself and then the factorial of the number which is obtained by subtracting 1 from this number. So if we'll do that, we will obtain 0 factorial. So this is 4 into 3 into 2 into 1 into 0 factorial, and we can't go beyond 0, because if we try to subtract anything from 0, we will obtain a negative number, and then that would create a big blunder. So then this is the solution. They say that okay, fine, you need not to go beyond 0 or towards the negative numbers. They have given us the value that 0 factorial is 1. So simply we get 4 into 3 into 2 into 1 into 1. So what do we get? That's the 24. So always what do we conclude is that whatever number whose factorial you want to find, the factorial, if I consider generally that n is a number, so n factorial obtained would always be greater than the number itself. Now you know we were trying to find factorial of 4, number 4. But what is factorial of 4? That is 24. 24 is greater than 4. If we take 5 factorial, then it comes out to be 120. Again, 5 factorial is greater than 5. 3 factorial is greater than 3. So, all in all, whenever we find factorial of a number, that is always greater than the number itself, or it could be same only in the cases when we have 1, because 1 factorial is 1, or if we have even 2 factorial, then that is also 2. So it's just these two cases which we can definitely ignore. But other than these, all the number that we have, we will always obtain the factorial value greater than the number itself. Now the thing is that the factorial of a number is most of the time greater than the number itself, exceptions being 1 and 2. When we have smaller numbers, finding factorial is easier. It's fine if we have number 7, number 8, number 9, number 10. Okay, we can find the factorial by simply multiplying all the numbers that we obtain. But what if we have a very large number? And in statistical physics and thermodynamics, we talk of atoms, atoms per meter cube. And you must be knowing that there is a number called Avogadro's number. So most of the time, the number of atoms present per unit of volume, we consider them to be 6.023 into 10 raised per 23. That much greater number. Such a great number it is. And in fact, if we talk of any of the atoms or molecules, stuff like that, the counting is not even in hundreds or 200, it's really large number. And if we have a really large number, suppose if we have 500 atoms in a particular volume, and if we have to find the factorial, and we will start doing 500 into 499 factorial, and then you would say 500 into 499 into 498 factorial, and so on. If you do, then the calculation would be really complex, and it would consume a lot of time. So this is a problem. If we go through the standard way of solving factorial, then things get tedious if we have a very large number. So for that case, Stirling formula is a great help. Stirling's formula, it gives us an approximation, a really good formula, which we can use if we have very large number. In fact, we can use it with any numbers and we would obtain the correct result. How do we do that? What is the Stirling formula? We are going to study now. So the thing is that this is a method also known as Stirling's approximation, a method for approximating values of large factorials. Whenever we have a really large number, we can make use of this formula. So this is of great help, especially in physics, especially in statistical physics and thermodynamics, where we deal with large number of atoms or molecules. Now, what does it say? The mathematical statement of Stirling formula is that for a very large value of n, if the number is really large, because if we have a small number, then we really need not to use this formula, because we can simply do the multiplication and get the answer. But if the number gets really large and we have to make some approximations, so that's why we also call it Stirling's approximation, because whenever, see, you can see here, this is natural logarithm. So when these things are introduced, that means you are using some sort of approximation. So here, this number, whatsoever number is there, whose factorial you want to find, and of course it has to be really large number, then what does that mean is that if you take the natural log of the factorial of that number, that would be simply equal to that number multiplied with natural log of the number, and then you just subtract this whole quantity like this. You just take the number, subtract it from this whole quantity, and afterwards what you have to do is, obviously you have to remove this natural log. How would you do that? You will simply take the anti-log and then you would get the value of this n factorial. But still it's really easy because we have log tables available to us. We can find natural logarithm of any number. So all you have to do is, see, in this formula there is no factorial involved. You are not saying any factorial here. See, this section, no factorial is there. It means this formula is such a good approximation of factorial of a number that it has simply removed the factorial, and all we have is simply the number. So you just take the number, you just take the natural log of the number, multiply the both, and then subtract the number from that product, and you will get the natural log. It's not that people often confuse that whatever answer is obtained here, they consider it to be equal to n factorial. But no, actually it is equal to natural log of n factorial. And if you want to find n factorial, then you have to take the antilog of this ln n factorial. Then you would actually obtain what is the exact value. But still, it's not a tough task, especially if the number is really great. Suppose this is the number, then I think doing this little bit of maths won't cost us much. That is much easier. So how did he actually obtain this expression? Let's see that. Let's start proving it. So we know that when we have to find factorial of any number, what do? We simply keep on multiplying the number with the number one less from it, and it just continues. So it will continue till we reach 1. So we can write here 3, 2 and 1. This is the expression. No matter what number you have, we will get this expression. So what if we have to find log natural? If we take log natural here, it means we have to take log natural here. So first I'm just going to write all this inside a big square bracket. Now if I open it, what do we get? Now this is log natural of n, then we have log natural of n minus 1, then log natural of n minus 2. We have a formula which states that if we have log of mn, then that is simply equal to log of m plus log of n. We can use this thing here. If we use this thing here, so we need not to write that ln of all this multiplied. We can simply write the addition forms ln n plus ln n minus 1 plus ln n minus 2, and then of course there will be plus. That would be ln 3 plus ln 2 plus ln 1. This is the thing, and we have used this formula here. Now this thing that we have mentioned, this whole summation, see we are just adding all these quantities. So how can we express this? In general, we can express it that ln n factorial is equal to, now this is sum of all the quantities, and we have a symbol for that, which is summation. Summation from, so in general, see this is changing, this is changing everywhere. So we are going to write ln x, okay? And now that x is what? If you start from the lowest quantity, what is the lowest quantity here? Suppose this n factorial is basically you are finding 20 factorial. So this n would be 20, this would be 19, this would be 18, and so on up to 1. So the lowest quantity is 1 and highest quantity is the number whose factorial you are finding. So here we are going to write x is equal to 1 to x is equal to n, the number whose factorial we have to find. Once again, you have to remember that this formula, this approximation is for large values of factorial. Now here, the n involved, we are considering it to be a really large number. So we have obtained this as our equation 1, and now Stirling showed that when n is really large, then we can write down this right hand side of the equation in the following manner. And what is that manner? See here, ln n factorial is as it is, left hand side is the same, but now this right hand side we have replaced sigma by integration, by an integral. So this becomes like this. We are replacing sigma by, why have we done this? Basically, this summation is for discrete numbers. The summation that we talk of, this is for discrete numbers. and this integral is for continuous. So now discrete number we talk of where we go for summation when we can actually count the numbers. They are countable. They're simply just like 1, 2, 3, 4, 5, 6 and so on. But when the quantity is really large, then it's really difficult to count all those numbers. See, suppose if you have a heap of grains, there will be so many grains. And then if you start counting each one of them, then that is an impossible task. So what do we do there? We actually consider it to be a continuous quantity and we try to take the integral. We try to approximate the things. So here and also the number can be in between also. It could be 1.4, it could be 1.7, it could be 28.9, it could be 304.2, number could be any. So basically when we have really large number, we prefer integration over this summation. Summation is for discrete number and when we are actually able to count those numbers. But when it's a continuous stuff, numbers can be any and really large number where it is not possible to count all the numbers, then we have to make use of integral. Then all we need, because in integral what do we need to know? All we need to know is the lower limit and the upper limit, and then we can simply integrate. So we can use some idea. We have the idea for lower limit, that could be 1, that just 1 grain if we are talking of a heap of grain. And then upper limit we can say that okay, these many grains are possible, and then we would simply integrate it. That if suppose now this heap is there and we are not going to count each and every grain out of it. We can simply say that okay, this particular sack is a 2 kg sack. So how many grains can come inside? In that case, all we need to do is take the integration instead of summation. We are not going to count how many grains would actually fill this sack. We will use approximation, that from 0 kg to 2 kg, and then we'll fill whatever function or whatever quantity we will take, and then we'll solve the integral. And the integration always give us approximate value most of the time, especially when number is really large. See, for small quantities everything is fixed because we can count them, and otherwise also just by simple calculation we can get the actual accurate result. But the things get complex when we have really large number. So even if we talk of integration, it's not that integration would give you an accurate result. Plus minus 1, plus minus 10 would be there, but still it gives an approximate value. And remember that this is basically we are doing Stirling formula, which is also known as Stirling's approximation. So it will simply approximate the value. It might change, it might vary, but still you will be near the accurate one. Okay, so this is the reason that when the number gets really large, we have to replace summation sigma by an integral. All right, now just solve this integral. So we had that the number of particles would be the least quantity would be 1 and the maximum is the number itself. So here also the lower limit is going to be 1 and the upper limit is going to be n, and then this quantity would stay the same. So here L and X, and now this is integral, and X is the number which is varying from 1 to n. So the integration would be with respect to x. So here we are going to write down dx. This is the rule. Next would be 1 to n ln x. We can multiply 1 here because that would help us in calculation. So I have just multiplied 1 here. Definitely the quantity would remain the same. But now here you see we have two quantities, ln x and 1. Two quantities within an integral. So we have to perform the integration by parts. We have two quantities now, and now we will use integration by parts to solve it. So what do we get? Integration of first, here this is the first quantity, okay. This is the second one. So integration of first and the second one as it is, or you can use either way. That first function, if you are going to consider, you can consider this as it is. So let me write it that way. It's just the way how we remember. So most of the time we remember it like first function as it is and integration of second function. So in that case, this is my first function and this is my second function. Okay. So if we say first function as it is, then integration of second function. So what would be integration of 1? That would give us x, because we are integrating with respect to x. Okay. And then we have to show the limits as well, because we haven't put them yet. And then minus sign, then the integration of derivative of first function. Now what is derivative of first function? We have d if log of x dx, that is equal to 1 by x. Okay, this is the thing. So this we are going to use. So derivative of first function, that would give us x, and integration of second function, that would again give us x, and then dx as it is, and again the limits. So what do we get now? If we have to substitute the values, so here first we will substitute n ln n minus 1 ln 1, right? And then, and here let me use the standard way of representation that we often use. Here I'm going to put bars. The moment I don't substitute the values, let me use the bars. Okay, so this is the value, and then here what do we have? It's simply 1 dx. So that would give me n ln n minus, now what is this? ln of 1 is 0. These are the formula that we are using, this one and this one. Ln of 1 is 0, so this term would be 0 now. And then here this would give us, now since log natural of 1 is 0, we are left with n ln n here. And then again we have to substitute the limits in this case, so that would be n minus 1. This is the thing. Now we know that n is really large. We can write n minus 1 as n, approximately equal to n. See, this is Stirling's approximation, so at each and every step we are just approximating. First approximation that we did was replacing sigma, summation, by integration. We did integration instead of summation. That is the first approximation that we used. And then second one was that instead of n minus 1, we can write it as n. And here, because why? See, if you talk of a less number, then this is wrong. We cannot write that 2 is approximately equal to 3. This is wrong. But if we have a really large number, 10 raised power 23, then 10 raised power 23 minus 1, they are approximately same, approximately equal. So we have to remember this thing, that we are doing this, or this particular formula is specifically for really large numbers. So when we have large numbers, we can make use of such approximations. So even if you find the value of 10 raised by 23 and if you just subtract 1 from such a big number, it will not lead to a big difference. But for small numbers, definitely this is not possible. That would be considered as wrong. Okay. So this is the approximation that we have used. So then what we are left with? In that case, we started with ln n factorial. And now if we replace n minus 1 by simply n, so we have ln n minus n. And this is Stirling's formula. So this is it. This is our final result. So thanks a lot for watching this video. This video